Alright, welcome everybody. Today we're going to talk about diffusion and effusion. And to understand what this is, we need to think about gas particles and how they move. And so the idea is that if I were to have particles in a container over here, and there was an opening in that container, just get rid of that line, there was an opening in that container, that the gas would start to come out of the container. And it would eventually, completely fill whatever container was outside of it. This is diffusion. Effusion is if I were to make this opening a tiny little pinhole and have the gas leak out of that tiny little pinhole. But either way, the gas movement is from where there is a high concentration of gas to where there's either no or a low concentration of gases. Diffusion and effusion happens, naturally. They'll say on their, based on their own accord, the gases will spread out. It's against gravity. It just happens naturally. And so gases will go from where there is gas to where there's no gas, and you can see that in the diagram that I drew. I'll also show you a nice video for this, and here's, if you want to go to this YouTube link, this gives you an idea of the diffusion of gases, but we'll actually watch that in class. Now there is math behind this, and the math relates to what's known as the rate of diffusion. And you could use it for effusion as well. Now gases, they move based on their masses, and the idea is that the higher the mass, the lower the rate. It's inverse. And so you could kind of think about it like this. The rate that a gas moves at is inverse to the square root of its GFM. So again, the higher the mass, the slower the rate. Now there's Graham's law of diffusion, and Graham's law of diffusion relates two gases to one another. And so it looks like this. The rate of gas 1 compared to the rate of gas 2. Their rate of diffusion is equal to the square root of the Graham formula mass of 2 over the Graham formula mass of 1. So you can see they're inverse. The rate of 2, Graham formula mass of 2, rate of 1, Graham formula mass of 1. So now you look at this and you're like, well, how would I do a problem? Well, let's say that we had two gases like hydrogen and oxygen, and I want to compare them. Well, what's the rate of hydrogen to the rate of oxygen? Well, we use their Graham formula masses. Oxygen's Graham formula mass is 32, hydrogen is 2. So now I just say, all right, square root of 16. That would give me 4. What this is telling me is that the rate of hydrogen, its diffusion, is 4 times the rate of oxygen. If hydrogen is moving at a rate of 10 meters per second, then oxygen will be moving at a slower rate, 1/4 of it, 2.5 meters per second. They're relative rates to one another. So I'll show you the demo. This is the law of diffusion and effusion, Graham's law. I want to pull things back to the beginning of the chapter when we did KMT. And I say this in class a lot. What are the ideas behind KMT? The kinetic molecular theory. And the whole idea behind this, if we look at how gases behave, we can explain gas behavior based on their particle nature. So remember, we have the straight line motion, we have no IMFs, we have elastic collisions, we have no molecular volume, and we have the relationship between temperature increasing and kinetic energy increasing. When gases follow these rules, these KMT rules, they behave ideally. And they're called ideal gases. And you've seen this come up, like ideal gas law. Well, we have gases behaving ideally. How does a gas behave ideally? Well, you cannot liquefy it. It follows the gas laws. These are the things that make a gas ideal. Gases generally behave pretty ideal. That's why we use the ideal gas laws and we can get away with it. And it's like an ideal chemistry student in the sense that, like, if I were to check off all the things that would make a chemistry student ideal, I would say, well, they do their homework, they come to class, like they show up for extra help, they get hundreds on tests, all these things you could check off, yeah, I'm an ideal chemistry student. But we know that there's no such thing as a truly ideal chemistry student. Ideal chemistry students will do something called deviate from ideal. Maybe they'll get a 90 on a test, or maybe they won't hand in a homework or complete a lab, or maybe they won't come to class or extra help. And so when we see with, gases deviating, they don't follow these postulates like they should. And so these are called deviation from ideals. This is a real gas behavior. And so when we have an ideal gas, we assume the most important things is that there's no IMFs and that there's no molecular volume. Well, it turns out that these two things are where the real problems lie. When we have a real gas, they do have IMFs, and they do have volume. And that becomes a problem. And so, real gases can be liquefied. And that is what we have to worry about when we have real gases that are going to become liquefied. And so the thing is, though, is that we can manipulate the gases with the conditions. So if we want the best conditions to keep a gas ideal, we would, 1, want low pressure, and 2, high temperature. I like to think of this like my ideal vacation. Low pressure, nobody telling me what to do. High temperature, I'm relaxing in the sun. I can do whatever I want. Low pressure, high temperature, just relaxing, chilling. I need a vacation. So my best conditions, keeping it ideal, low pressure, high temperature. Now, why does this matter? Why is this true? Well, if you have low pressure, that means that you have a large volume. And that means that you would have less intermolecular forces. The gases would be far apart. And their molecular volume would be less important. And high temperature, here the gas particles move fast. And here again, we can overcome IMFs. For intermolecular forces to work, you need to have the particles close together and moving slowly. That's how they'll stick together. If they're moving fast and they're far apart, those IMFs become less and less important. Now, the other thing is the type of gas. Best type of gas would be the lightest gas. And this is generally because it's small. And that means that it has less molecular volume. So when they say, what gas is most ideal or most likely to be ideal, you're going to go with the lightest ones, hydrogen and helium. You also want a gas that's nonpolar, so that it doesn't have intermolecular forces, or it has really weak ones. So we have nonpolar gases, weak intermolecular forces. Hydrogen and helium are our best bet. And we can see that in their boiling points. Hydrogen boils at 4 Kelvin. The coldest temperature is 0 Kelvin. So keep this in mind. These are types of questions that you get. What's the best conditions for an ideal gas? What type of gas is most ideal? That kind of thing. Here's just a graph showing you the effects of temperature and pressure. And so what they do is they increase pressure down here on the x-axis, and then they graph this at different temperatures, 1,000, 500, 200. So an ideal gas, its number of moles would always equal 1, because PV over RT, it would follow the ideal gas law exactly, and it would remain true to the ideal gas law. If you have a very high temperature, you can see that at 1,000 Kelvin, that's a high temperature here, that the gas remains pretty true to that ideal gas line. But if I lower the temperature to 500, what you'll notice is that as I increase the pressure, the gas deviates pretty severely from the ideal behavior. And that's because the molecules will start to liquefy. If we go to 200, we even get a more severe effect. So what you can see is that the temperature has an effect. The higher the temperature, the more ideal. The pressure has an effect. All these gases, even at the lowest temperatures, even at 200, when we're at low pressure here, at close to 0 atmospheres, like 1 atmosphere, they're all really close to that line. And you can also see the effect of, how ideal the gas is on its molar volume. And so here's molar volume at STP, 273 Kelvin and 1 atmosphere. This is actually relatively high temperature per se. It's not, it's not crazy like hot, but it's high for a gas, and 1 atmosphere. And what they did was they graphed different gases. And the ideal gas will have an exact volume of 22.4 liters. And you can see that the lightest gases, like hydrogen and helium, they are almost exactly that. If we have a heavier gas like chlorine has, a number that deviates from that. But you can see that all these gases at that temperature and pressure, high temperature, low pressure, they pretty much follow the ideal gas. So what I want you to take away from this is that ideal gases, it's a theory. No gas is truly ideal, but the conditions that we study gases at, gases will behave ideally. Just like with an ideal chemistry student, if I load on a lot of work or make the test really hard, you'll deviate from being ideal. But if we keep things status quo, then you'll remain close to the ideal chemistry student, especially if you're an honors student. So gases, we use the ideal gas laws because they work. Remember that if you take a gas and you put it under high pressure and low temperature, it'll deviate from ideal gas behavior. The best gas to stay ideal will be hydrogen and helium. The lightest gases, the ones with the least intermolecular forces and the smallest molecular volume. All right, well, you've seen gas laws, and feel free to rewatch any of the videos and really go through them, make sure you know what I'm talking about. All right, thanks again for watching, and see you for solutions next.